Hello, thank you for listening to my presentation. My name is Mohamad. I'm a neurosurgical resident here at Western, and I'm currently completing graduate training with Dr. Julio Martinez at the Robarts Research Institute. I'll be presenting our work looking at multiplexing neuronal ensembles in the primate prefrontal cortex during virtual reality navigation. Now, the prefrontal cortex contributes to cognitive control, which is considered the ability to plan thought and action in accordance with internal goals. It's hypothesized to build mental representations of goals and the means to achieve them. Clinically, patients with prefrontal cortical lesions have been demonstrated to have impaired attention, motivation, working memory, rule learning, and planning. The prefrontal cortex has also been implicated in many psychiatric diseases with imaging and histological studies. Also, many symptoms involved in these diseases have been suggested to arise from a dysfunction in the prefrontal cortex. Ultimately, these symptoms may result from a deficit in the prefrontal cortex's ability to build mental representations of goals and the means to achieve them. We're interested in studying the neural basis of these mental representations. The prefrontal cortex is considerably expanded in anthropoid primates, which has served as a model to study the neural basis of these mental representations. However, they have been explored in simple tasks with limited ethological value in the past. Therefore, we sought to use virtual reality in a navigation task to investigate the neural dynamics of these mental representations. We trained two rhesus macaques to perform a navigation task using a joystick. The monkeys navigate in an X maze with a typical trajectory as outlined in the middle figure. As the monkeys approach the corridor, the walls of the maze change color to either wood or steel. Each context is associated with a color that provides the monkey with a larger reward. For example, in this case, wood is associated with cayenne. As it approaches the end of the maze, two colored discs appear at random sides. This is referred to as the goal onset. The monkey must then choose the appropriate goal to navigate to. The instance when the monkey first initiates a movement is referred to as the decision onset. We implanted these monkeys with microelectrode arrays in the lateral prefrontal cortex. Each array contains 96 channels, and we simultaneously recorded from many neurons. We analyzed the neural activity in 400 millisecond windows as the monkey traversed the maze. For each recorded neuron, we performed a two-way ANOVA to investigate alterations of firing rates due to context and side. We then studied the whole population of neurons simultaneously recorded. We trained a machine learning algorithm to predict the context and chosen side based only on the neural activity. Here we plot the proportion of neurons with significant information for context or side around the onset of the goal. This is when the two colors appear and the monkey must make a decision on which side to choose. We can see that initially neurons have information about the context, that is, the color of the wall. This occurs around 600 milliseconds before the goal comes on. Shortly after the goal onset, many neurons have mixed selectivity. This means they simultaneously code for context or side. For example, a neuron that fires more when the context is steel and the chosen side is right would have mixed selectivity. Then many neurons encode side information. The figure on the right represents each neuron's selectivity on the y-axis at every point in time. This figure demonstrates that many neurons change their selectivity at different points during the task. For instance, many neurons that were initially tuned to context become tuned to side after. Next, we trained a support vector machine to predict the context and side of a given trial based on the population neural activity. The y-axis represents a decoding accuracy, and the x-axis is time. At the onset of the context, when the walls change color, there does not appear to be any context or side information. Of course, the monkey has not decided on the side at this point, so this is expected. However, interestingly, there is no context information despite the fact that the walls change color at this point. Looking at when the goal comes on, we're able to decode the context with 80 to 90% accuracy. In fact, this occurs before the goal comes on. After about 600 milliseconds, we can start to decode the chosen side with close to 90% accuracy. Finally, when centering around the onset of the decision, we demonstrate we can decode the monkey's chosen side with greater than 90% accuracy prior to the decision onset. Overall, we propose that these neural ensembles allow primates to build mental representations of the task elements required to achieve their goal. We demonstrate that many neurons are multiplexing, meaning they can represent different task elements. For instance, many neurons that initially encode for context later encode for side. Also, these representations appear to be fluid or brought online when required. For instance, the context information is not present when the context comes on, but is present when the goal comes on, which is when it is required to make the decision. Understanding the neurophysiology of the prefrontal cortex can allow us to develop hypotheses about the pathophysiology of the neurological and psychiatric symptoms previously discussed. Further work is required to investigate mental representations of prefrontal cortical neurons in these patients. These abstract mental representations can also be decoded and potentially used as signals in brain-machine interface to benefit patients with quadriplegia or locked-in syndrome. Thank you for listening.